All right, so here is video number 2 in learning target number 12. This one is going to talk about instantaneous rate. So average rate, as we saw in the previous video, is pretty easy to calculate. Change of concentration over change of time. However, that's great if the rate stays constant during the course of a reaction. Most of the time that doesn't happen, so things get a little bit more complicated. Let's see what we mean by that. So let's take a look at this graph to the right here. This is a good graph that would depict what's happening to the calcium carbonate, that would be A here, over a period of time. It's going to be what we call a zero-order reaction because the rate of change in concentration never changes throughout the course of a reaction. The calcium carbonate is going to decompose at the constantly steady rate. Of course, here we've got a particular equation that goes along with this graph. The relationship is linear, so if I've got change of concentration of A is going to take on the form mx plus b, but in this case it's going to be negative k times the time plus the initial concentration, which would be your y-intercept here. K tells us what's called the rate constant. K is going to be the rate constant. In a zero-order reaction, the slope of the line is going to be constant just because it's a linear equation. And it's equal to the average rate of the particular chemical reaction that we're studying. And it's a zero order because that rate just never changes. If I was to take the derivative of this, I would get the derivative to the 0th power, or 1, because I would have no slope. So this is why it's called a zero-order reaction. Most reactions aren't like this, however, and since they're not like this, we have to talk about instantaneous rate. So if we have a reaction where the change in concentration does not remain constant over time, we can't use average rate, and we can see why here. So in this particular equation, this particular reaction is what we call first order. That means that as the concentration proceeds over time, the change in concentration is going to halve itself every period of time that you measure. First order once again. If I was to try to find the rate of reaction here using the average rate, I'd find the slope of a line that begins at t equals 0 to t equals final. And you'll notice here that if I drew a straight line, that would nowhere near be explaining the shape of this particular graph. So here we need to find what's called the instantaneous rate, where the instantaneous rate is going to be the rate of a reaction at a particular point in time. And it's represented by a tangent line that is going to be tangent to one particular point in time on your graph. And we're going to look to see what this looks like in just a moment. So the instantaneous rate finds the rate of the reaction at exactly one moment in time. So what we've got here is a graph of a first order reaction, which is going to be exponential decay. The rate is going to halve itself every single moment in time here through a rate constant. We'll talk more about that in another learning target. Let's say I want to find the rate of reaction at exactly 25 minutes. We're going to use 25 minutes here. Most of the time we use seconds, but this is the best graph I could find. On this graph here, it says here monomer. When we do organic chemistry, you'll find out what monomer means. One part of a carbon chain. No big deal there. You're also going to see, complete side note, this watermark on your screen, and that's because your dip of a teacher forgot to pay for her Smartboard software upgrade, so good job, Miss J. So just ignore this, this Smart Notebook Basic version, or make fun of me for it. I don't. So what I'm going to do is I'm going to find 25 minutes on the graph. I'm going to assume it's about right there. And I'm going to draw a line that is tangent to that point at 25 minutes. So this is the cheap and easy way to do a derivative. I'm going to hold that ruler up to the graph where you see my ruler only touches that 25-minute mark at that one point. So the slope of that line is going to give me the rate of reaction at exactly 25 minutes. So I'm going to draw that particular line here. I'm going to trace it right down my ruler. And then what I'm going to do is I'm going to take this ruler away, go away. And because I have a beauty of technology, I can just adjust it just a touch just to show that this red line is tangent to t equals 25 minutes. And now I'm going to find the slope of that line. The slope of that line is going to tell me the rate of reaction at exactly one moment in time, 25 minutes. So I'm going to do rise over run. So here's my rise. And here's my run. And then I'm going to start to do some estimating here. And with this method, estimation works really well. If you do this on an IB exam, just make sure that you estimate as closely as possible. They do not knock you off for not getting their values. Okay, so let's estimate our run first here. So I'm going to say that this is going to be at 0.0. This I'm going to say is about let's say 55. So the change in time is going to be 55 seconds, give or take. And then I'm going to estimate my change in concentration. And this is moles per liter. That's what big capital M stands for. I'm going to say that this is about 4.75 there. And I'm going to say that this is about, let's say, 1.8. So this rise is going to be 4.75 minus 1.80. And I'm going to have a change in my rise of about 2.95 moles per liter. So at 25 minutes, and this is the only time that this rate will be this particular value, is going to be the change in concentration over the change in time. And that's going to get me 2.95 divided by 55. And when I solve this on my calculator, and I'm going to say 2.95 divided by 55, I'm going to get a rate of reaction of 0.054 moles per liter per second. So this particular monomer, one piece of the carbon chain, is decaying at 0.054 moles per liter for every second for every minute, excuse me, at 25 minutes. And that's the only time that that's going to happen. Now, this is the cheap and easy way to do a derivative for one moment in time in a graph. And you might also recognize this from calculus or from honors physics when we found instantaneous velocity or instantaneous acceleration the exact same way, if you remember back that far. All right, so this was your example on how to find instantaneous rate. The next thing we're going to do is find the initial rate. And over and out here.